Classical mechanics and quantum mechanics are two fundamental theories that describe the behavior of physical systems. While both theories are concerned with understanding the laws of nature, they operate on different scales and have distinct principles and mathematical formalisms. Classical mechanics, also known as Newtonian mechanics, was developed by Sir Isaac Newton in the 17th century and provides an accurate description of the motion of macroscopic objects such as planets, cars, and projectiles. It is based on the concept of classical determinism, where the future state of a system can be precisely determined if its initial conditions and the forces acting upon it are known. Classical mechanics is governed by Newton's laws of motion, which relate the motion of an object to the forces acting on it. These laws can be used to predict the trajectory of objects and analyze their interactions. On the other hand, quantum mechanics is a more recent theory developed in the early 20th century to explain the behavior of microscopic particles such as atoms and subatomic particles like electrons and photons. Unlike classical mechanics, quantum mechanics introduces the concept of wave-particle duality, which suggests that particles can exhibit both wave-like and particle-like properties. Quantum mechanics also introduces the principle of uncertainty, as described by Heisenberg's uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. Quantum mechanics is described mathematically using wave functions and operators, with the Schrödinger equation being the central equation that determines the time evolution of a quantum system. The wave function of a quantum system contains all the information about the probabilities of different outcomes when a measurement is made. The measurement process itself is probabilistic, and the act of measuring a quantum system typically causes a collapse of the wave function into one of the possible measurement outcomes. Another important aspect of quantum mechanics is the concept of superposition, which states that quantum systems can exist in a combination of multiple states simultaneously. This leads to phenomena like quantum entanglement, where two or more particles become correlated in such a way that the state of one particle cannot be described independently of the state of the other, even if they are far apart. While classical mechanics provides accurate predictions for most everyday objects and situations, quantum mechanics is necessary to describe and understand the behavior of microscopic particles and systems. In situations where quantum effects become significant, such as in the realm of atoms, molecules, and subatomic particles, classical mechanics fails to provide an accurate description. On the other hand, quantum mechanics reduces to classical mechanics in the macroscopic limit, where quantum effects become negligible.